All right, we're continuing with Chapter 4 in the statistics textbook. In this video, we're going to go through Section 4.3, the average and the histogram. So 2 videos ago, we went through Section 4.2, which was the introduction to the average. And I actually made an assumption that was incorrect. And unfortunately, I repeated this assumption many times over the course of that video. But even so, I'm not remaking the video. Bring on the negative comments. So the assumption that I made was that the center of area of a histogram sits at the average. So just a reminder, with a histogram, you might tend to think, well, there's an X and a Y axis, so there's like 2 sets of variables associated with a histogram. No. Remember, a general histogram is created from one set of values. So for example, this batting averages histogram that we created, we made a distribution table and used that distribution table to make the histogram. Here's the raw data we pulled from the sportsreference.com, but the histogram we made was just based on the batting averages. There were 156 batting averages going from like 1880 something to 2024. This list of numbers, that's it. That's the data behind the histogram, just this list of numbers. I just want to point that out because we're going to be talking about the median and the average in conjunction with a histogram. And it's easy to look at a histogram and think, well, there's 2 sets of numbers, right? An X and a Y axis. You've got variables on the X axis and then other variables on the Y axis. Not with a histogram. It's one set of numbers. The vertical axis is just more of representing in a sense, like the count of how many of those numbers are contained within a certain interval. So again, as we go through this section, when they're talking about the average of a histogram or the median or the standard deviation, when you look at a histogram, you can think about one list of numbers, a list of batting averages. You know, you can take the average of these batting averages, add them up, divide by the number of data points. You can get the median of this list. What's the middle point? Okay. And so again, in the previous section, I was making the assumption that the point on the x-axis, because the x-axis is, this is the batting averages, right, on the x-axis. The point on the x-axis where there's half of the histogram area to the left and half to the right, I was saying that's the average. And that was an incorrect assumption. That is not necessarily where the average is. That is where the median is, though. And I wish I would have picked that up. That makes perfect sense because the areas are proportional to the number of data points. The number of data points. That's the definition of a histogram. So if there's 50% of the area on the left and there's 50% of the area on the right, that means there's 50% of the data points on the left, 50% of the data points on the right. That's exactly what median means. 50% of the data points. But in the previous section, we talked about how the average does not necessarily have to be the median. So for example, if we've got the list 1, 2, 3, okay, here's the list of numbers. Well, what's the median? 2. There's 1 data point on the left, 1 data point on the right. What's the average? It's also 2. 6 divided by 3 plus 2 is 5, plus 1 is 6. 6 divided by 3 is 2. But you can just see 2 is halfway between 3 and 1. Okay, but what if I change this to 6? What's the median? Well, it's still 2. There's 1 data point on the left, 1 data point on the right. But what's the average? 6, 7, 8, 9 divided by 2, 4.5. So clearly the median and the average don't always have to be the same thing. But what I should have realized is that based on the meaning of a histogram, the fundamental property of a histogram is that the areas are proportional to the number of data points. The point where there's half the area on the left and half the area on the right, that's the median, not the average, not necessarily the average. All right, so it starts off saying this section will indicate how the average and the median are related to histograms. To begin with an example, there were 2,696 women age 18 and over in Haynes 5. So in the previous section, we were talking about these Haynes studies. Their average weight was 164 pounds. So in Haynes 5 and the 0304 Haynes 5, there were 2,696 women age 18 and over. So that's all of the women in the study. And their average weight was 164 pounds. So you can see If we're just, they asked the women, these are all the women in the study, they asked them a bunch of different questions, but if we're just looking at weight, then that's just one list of numbers. There's 2,696 weights. Okay, you can make a histogram out of that. You could take the average of that. You could take the standard deviation of that, etc. The median. It is natural to guess that 50% of them were above average in weight and 50% were below average. Well, I don't know how natural that is. To me, I would have a sense that that's not necessarily the case. Well, no, I take that back. Right. If you take the average, you might tend to think that the meaning of the average is that 50% of the women were above that weight, 50% were below. I could see how you could think that. However, this guess is somewhat off. In fact, only 41% were above average and 59% were below average of the data points of the women. Figure 4 shows a histogram for the data. The average is marked by a vertical line. Okay, so here's the average weight. Okay, now what they're saying is 41% were above the average and 59% were below the average. So what does that mean? Based on the definition of the histogram, that means that the total area above this line is 41% and the total area below this line is 59% relative to the entire area, the area of this entire chart. How is this possible? To find out, it is easiest to start with some hypothetical data. The list 1, 2, 2, 3. So yeah, we just did an example of this. But let's go through their example as well. So the list 1, 2, 2, 3, the histogram for this list is symmetric about the value 2. So you can take any list of numbers and do a histogram. And here's that histogram for this list. You've got 50% of the values are 2s, 25% are 1s, and 25% are 3s. It's symmetrical. So this histogram is symmetrical. And what they're saying is, if the histogram is symmetric around a value, that value equals the average. And also, it's okay, furthermore, half the area under the histogram lies to the left of that value and half to the right, which that's also where the median is. So if a histogram is symmetrical, then at the midpoint, that's what it's going to be symmetrical about. That's obviously the median, because if it's symmetrical and the midpoint's going to be where the center of area is, so that's obviously the median. But then because it's symmetrical, that also means that it's the average as well. So what they're saying is the median, so like looking at this histogram, the median and the average don't line up because 59% of the data points were below average, 41% were above, meaning that the median is actually somewhere over here. And the main reason why this happens, that the median and the average don't line up, is because the histogram isn't symmetrical. This is definitely not symmetrical. It's like skewed to the left. What happens when the value 3 on this list of numbers is increased to, say, 5? That's the example we showed. Or 7. As shown in figure 6, the rectangle over that value moves off to the right, destroying the symmetry. Okay, so let's look at figure 6. So here's the histogram for the new list. This value here, the value at 3, is moved off to the right. And so obviously the symmetry is gone, but the center of area is still here. Half the area to the left, half the area to the right. You add up this area plus this area, that's equal to this area plus this area. If you change that value from 5 to 7, the average moves out even more. And so what they want to indicate here is that you can think about the average as, where does this rod need to be placed to balance the areas, right? It's like a seesaw. They show a seesaw here. Yes, here, still half the area is to the left of this line, half to the right. But if you put this rod at the median, it's not going to balance. The balance point is the average. The center of area is the median. Now, this is a little different because you don't have a continuous area in these cases. You don't have one unbroken area. But we saw here in this example that here was an unbroken area and the average and the median didn't line up. Why is that? Well, the median is somewhere over here. But if we try to balance this histogram here, so imagine that all of these rectangles are made up of the same material, like steel, the exact same material. This is more steel than this because it's taller, but it's the same material. Why won't it balance here? Because while these rectangles are smaller, they're way far off. They're spread out farther away from the group. That's what happens when you lose that symmetry, that when you go away from a curve like that and lose that symmetry, then you're naturally going to have points that are further away from the center being the median, than other points. So if you don't have that symmetry, then the median and the average aren't going to line up. Okay, so it says here a histogram balances when supported at the average. Balances. When you think about it balancing, then you're thinking about the average. When you're thinking about center of area, you're thinking about the median. If a histogram is symmetrical, then the median and the average are the same. Why is that? Well, because if it's symmetrical, the center point of the symmetry is where there's equal area to the left and equal area to the right, but that's also where it's going to balance. So it's giving the seesaw example. All this is trying to illustrate is how a less number of data values can carry more weight in terms of balancing if they're farther away from the median. So the median of a histogram is the value where with half the area to the left and half to the right. For all three histograms in figure 6, the median is 2. With the second and third histograms, the area to the right of the median is far away by comparison with the area to the left. Consequently, if you tried to balance one of those histograms at the median, it would tip to the right. More generally, the average is to the right of the median whenever the histogram has a long right-hand tail, as in figure 7. The weight histogram had an average of 164 pounds and a median of 155 pounds. The long right-hand tail is what made the average bigger than the median. Right, this is everything we just talked about, talking about this figure here, and they're saying it's this long tail here that strays away from the median that gives these blocks here that aren't that very tall, but it gives them more weight because they're farther away from the median. Okay, and so then in figure 7 here, they're just giving the general idea of, so if any histogram that's not symmetric, that means that you can take that to mean that the median and the mean and the average don't line up. If it's not symmetric in any way. But let's start with if it's symmetric, then the median and the average are the same point. But if it's not symmetric, if you look at the anti-symmetry and in general, the data points are kind of skewed to the left, then what that means is that the average is going to be greater than the median because the average needs to be able to support that. You call it in engineering a moment arm. It needs to support the data points that are farther away, because even though there's not a lot of them, they're farther away because of the anti-symmetry. So they're going to have more moment arm weight when you think about balancing. Right, a long wrench, you don't need as much force. And then for a histogram that's not symmetric, skewed to the right, the average is going to be to the left of the median. Because if it was at the median, then these data points out here, there's not a lot of them, but they'll still pull. They would pull down the balance because they're farther away. For another example, median family income in the U.S. in 2004 was about $54,000. The income histogram has a long right-hand tail, and the average was higher, $60,000. When dealing with long-tailed distributions, statisticians might use the median rather than the average if the average pays too much attention to the extreme tail of the distribution. Interesting. We return to this point in the next chapter. So what they're saying here is that the income histogram in the 04 study has a long right-hand tail. Why is that? Because, okay, if you have, your poverty level is over here and the wealthy are over here. Well, there's a smaller number of people that are wealthy, right? The old saying that a small number of people have the largest, amount of money, control the wealth or whatever. Well, this is a count. This is a count of how many people make this amount of money. The way this study is set up, they've surveyed a bunch of different people in the population and said, what's your income? And so there's not that many people that make this amount of money per year. So it's a lower it's a lower percentage of data points in this area. So it's it's a tail here, a right-hand tail. Whereas you've got poverty, probably the poverty level in this region, and then here's I guess the middle class, lower middle class. But okay, so what does this right-hand tail mean? You've got data points. There's not that many of these data points, but like they're saying, it's these very wealthy people, billionaires or whatever, multimillionaires. They're way out there. When you're going from lower middle class to wealthy, it's a big gap. So yes, it's not as many data points, but they're far out there. So as far as like the seesaw analogy, when it comes to the balance point, it pulls that balance point away from the median. The average needs to come out to balance the areas. If you think about all the area being the same material, it's all made of like steel. And it says here, which is interesting, in dealing with these types of distributions, statisticians, these long tail distributions, or I guess any kind of potentially antisymmetric distribution, statisticians might use the median rather than the average when they're reporting this to people. If the average pays too much attention to the extreme tail of the distribution. And we're going to talk about this point in the next chapter. All right, let's work some example problems.